After trees and binary trees and binary search trees, the next data structure, which is actually a tree, is binary heap, and that's what we are going to discuss in today's lecture. Binary heap, as the name suggests, binary, so it's a binary tree, and why we call it a heap we'll see in a while. So a binary heap is a binary tree with two properties. So one is the structure property. It's actually a completely filled binary tree. If you remember, we discussed the types of binary trees. So you have a complete binary tree in which all the levels are filled except the last level, and the last level might be partially filled, but it's filled in order from left to right. So that is one property it needs to have to be called a binary heap. A complete binary tree filled up to the last level. The last level can be partially filled, but it is filled in order from left to right. Then the other property is called as the heap order property. So in case of a binary search tree, you saw that the element in the root has all the elements smaller than it in the left subtree and all the elements greater than it in the right subtree. In case of heap, if the root has any element, let's say x, all the elements in the tree in the next level will be less than x. So including the root node of the left subtree and the root node of the right subtree. Or if it's the two types of heap, a max heap. If x will be the largest number in the whole tree, and the next level will have elements which are smaller than them, and the same property will apply in all the subtrees. Okay, or this x, the root value can be minimum, and all the elements below it will be greater than that. Okay, so we'll just see in an example. Since it's a complete binary tree except for the last level, we can use an array implementation because it will be efficient. We are filling level by level, only the last level will be partially filled, and we know all the intermediate spaces, there will be no empty spaces in between, so it will be efficiently used. So we can have an array, and you don't need to have a static array, you can have a dynamically allocated block of pointers which you will use as an array. Okay, so before I go here, let me show you the heap example. So the one on the left here is min heap. If you see, 13 is the element at the root, it is the least of all the elements in the tree. 21 and 16 are greater than 13. So if you see in the left subtree, 21 is the least of all the elements in the left subtree, and 16 is the least of all the elements in the right subtree. So the same will be true for all the subtrees. Okay, so in 21, the subtree rooted at 21, the left subtree is rooted at 24. 24 is less than 65 and 24 is less than 26. So on the right hand side, you see the opposite. The root element is the largest, or it's a maximum value element. Everything that is in the left and the right and the levels, as you go down, the elements will always be smaller than the root. Root will be the maximum of the left and the right subtree elements. So it doesn't matter in which order you could have this subtree, 16 subtree on the left and 21 subtree on the right. This doesn't need to be in order. The only order that needs to be followed is that the elements or the children of the root in case of a min heap are greater than the root, and in case of the max heap, the children of the root are smaller than the root. Okay, so let's go back. So this is a binary tree now, a completely filled binary tree, with the exception that the last level is not filled, and it follows this order. If it follows this order where the root element is the least of the left and the right subtree, and the same definition is followed recursively on all the subtrees, then it is a min heap. So this is the order property, and if the root is the maximum, it is a max heap. So when you do the implementation, you're either implementing min or max depending on your requirement. So like I said, since it's a completely filled binary search tree, we will use an array implementation. Also, if you see, the last level is partially filled here. So after 32, the next element, whatever comes, will be put here in this location. So it's not necessary the next element that comes will be the proper element to be placed here. By proper, what I mean is that this is a min heap, so whatever comes here should be greater than 31. So for example, I want to put 6 here. So if I put 6 straight away here, it will obviously go against the min heap property. So the next element has to go at this location, but if it does not fit the order property, then you can decide where it will best fit in the tree and move it there, and there is a procedure to do that. Okay, and same is the case for max heap. If you get, let's say if I put 6 here, in this case 6 is okay because it is a max heap. 6 can straight away go here, but let's say after 6, what I want to put here, I want to put, let's say I want to put 80. So I won't actually put 80 there because it's technically going against the max heap property, but when I have to put 80 here in this location, I'll first check, is 80, if I put 80 here, let me check its parent first. So I'll check 19, and if 80 is greater than 19, which cannot happen in a max heap, I'll say okay 19, you come down, and I'll say okay, let me try and put 80 here. I don't put it there, but I tried to put it there. And how would I know that putting 80 here is the right decision? So for that, I check the parent of this location. It's 20. So again, I feel no, 80 cannot go here because 80 is greater than 20. The root has to be greater in the max heap. So I'll say okay 20, you come down. Then let me try putting 80 here. Can I put 80 here? Let me check it first. So I check it against 40. No, 40 is smaller than 80, so 40 will come down, and eventually this space will be empty because I'm moving all these elements down. I moved 19 here, I moved 20 in the place of 19, I moved 40 in the place of 20, and eventually 80 will come here. And this is what we have to do in the implementation of heap. You'll see the same in case of deletion as well. So before we actually go into the implementation, let's see how we can define a heap so that we have a flexible heap definition, so that we are not restrained in terms of the number of elements it can carry or its capacity. So we define a structure called heap which has 3 elements. One is the capacity. So let's say I decide, let's say in the beginning I only think I'll need 100 elements in the heap, so I'll say the capacity of my heap is 100. As I'm building the heap, what is the current size? So I'll build the heap by putting the elements one by one. So the current size, let's say there are 20 elements at any particular point of time, size will have that 20. So if this is 100, this is the total size of the heap, and 20 is the current size basically. Then I also declare a pointer of type int. My heap is going to have int elements, so that is my type of heap. What is this pointer? This pointer will hold the base address of the array that I'm going to declare based on the capacity of the heap. So if as a programmer I decide, or I ask the user what is the capacity you want in the heap, you'll say 100. So I'll allocate a memory block of 100 integers, and the pointer of that, or the start pointer of that block, single block of 100 integer space, will be allocated to elements. And then I can use elements as an array because I have a continuous block of memory of size 100. Okay, so I'm declaring a dynamic array like this. Okay, if at any point of time I want to increase my capacity to say 200, then I can reallocate. I can use realloc. Whatever existing elements are there, they'll be copied in the new block, and the block size will be increased. So to do this, let's first write the initialize function for the heap. So my heap is a structure. Okay, then I define a structure heap, okay. Type def struct heap as pq. I have written pq, we mean a priority queue. Or you can, I'll explain later why heap is also a priority queue. So for now, let's name it pq. Okay. So to initialize, so that means when I write this statement pq, whenever I use pq, I will actually uh, declare a structure of this type. So I don't need many of these structures. I just need one structure that can hold the pointer to the array, which I'm going to use in my tree implementation or heap implementation. So I declare a pointer of this type of structure. So first I allocate memory for the structure. So malloc size of struct heap, and that pointer goes into h. So now h is the heap structure I have. Now I want, there are two let's go here first. What am I passing in the initialize function? This is the max number of elements that I expect to be there in the heap. So the block or the array that I allocate dynamically will be of size max elements into the size of integer. Okay, and that pointer will go in h to elements. Now the user passed max elements into this function, so that is what I will populate my capacity with. So if the user entered 100, my capacity is 100 now. My current size is 0 because I have nothing in the heap as of now, and I am putting a min value in the 0 location. So I'll explain to you why I'm putting a min value. If you remember, in the binary search tree or the binary tree implementation, we had two types of implementation. One was where I start with index 0, and the other one was where I start with index 1. This is actually starting from index 1. Why I have put a min value in 0? Min value is the least value, or it can, let's say, one less than the least value that you can have in the heap. We are going to uh, implement a min heap. Okay, so whatever is the minimum value the user can enter, let's say user can enter only 0 elements from 0 to, let's say, 2000. So minus 1 is one less than the minimum or the least value that the user can enter. So it's like a boundary condition for us. We'll see in a while. Okay, so what is insertion in the heap? So just before I go into the code, let's see. uh, let's see the min heap first here. Okay, so like I said, I want to insert something here in this heap. According to the heap structure property, the next element that you add should go in this location. So the example I've taken here, the next element that I want to add is 5. Okay, I'll explain this part later, but let me explain it to you on this figure first. So I have to insert 5 here. So I don't straight away go to this location and insert 5 here, because I know the size of the heap. I know what this location number is. I can just go and put 5 there, but I cannot simply put any number because I might destroy the heap order property. So I know I have to insert 5 at this location. I know the parent of this location. So before I actually insert 5, I check 5 against the parent. The parent is greater than 5, so I cannot put 5 below this because it's a min heap. So the parent will have to come down. Okay, so I will get, let me write here, I'll get 31 and I'll copy it in this location. So this location is filled, and currently I have a duplicate here. Okay, now I move, basically I move to the parent of this node. Now 31 is moved here. Let's say, can I put 5 here? To see that, I have to compare 5 with 21. Okay, so 5 is again less than 21, so 21 will have to move down. So 21 goes here, it overwrites. Okay, then let's say, can I put 5 here? No, because 5 is less than 13, so 13 will come here. And when I reach this point, can I put 5 here? What is the parent of 13? 13 is itself the root, but if you see, the parent of 13 is the location 0. The parent of 13 is actually 0, which is the minimum value. So 5, when you compare 5 with the least value is less than 5, so 5 will straight away go here. So if you see, if you have to visualize it this way. When I brought 31 down, I told you there's a duplicate of 31. You can just think you physically brought 31 down here. Okay, so this hole that I had actually created here, this moved here. Then when I compared 5 with the parent of this location, 21 had to move down, so this hole moved here. Then I compared 5 with the parent of this location, 13 came down, so the hole moved here. And this was the last location. There's nothing more to go in this upwards in this tree, so I put 5 in this hole. So I filled this hole. So insertion process in a heap is also known as percolate up. This hole, it moves up till it kind of stops at the right location, and then when it stops, then is the time you insert the element there. Okay, so let's do the same example and see what happens in the function. So is full h is a function that tells you if the heap is full. If it's full, the size is equal to the capacity of the heap, then it's full. Then let's say, what is the size at this time? How many elements are there? 4, 5, 6, 7, 8, 9, 10. There are 10 elements in the heap. The size is 10. Okay. Our next entry is going to be at size plus 1. So I initialize I to size plus 1. And then I check. I'm not inserting 5 anywhere. I am checking if 5 is less than the element present at location I by 2. What is I? I is 11. I by 2 is 5. The parent of location 11 is 5. 31 was the parent of this location. Is 5 less than 31? Yes, it is less than 31. So if it is less than 31, you go inside this for loop and you copy 31. I by 2 is the parent. I is the child. You remember, if n is the parent, 2n is the child. And if, let's say, x is the child, x by 2 will be the parent. So I copy 31 in this location, which is here. 31 goes here. And you go back in the for loop. What happens to I in the for loop? I changes from I to I by 2. So basically, earlier it was pointing to 11. I by 2 was 5. I was using I by 2 for comparison. Now I is set to I by 2, because if you remember in the figure here, now I have to compare 5 with the parent of 31 or this location. Okay, so what is the parent of 21? It was 31, it was 21. So again, I'll compare, I'll find it is less, 5 is less than 21. I'm not comparing 31 with 21. I'm comparing 5 with 21. It is less, so 21 will be copied in. 21 is at location 5 by 2, which is 2. So 5 by 2 is actually 2.5. We take the floor of that. So when you say for an integer, if you use division and you get a decimal point, it will be truncated. So 21 will be copied at location 5 and I will be set to I by 2, which is 5 by 2, which is this 2. Again, you'll check if 5 is less than the parent of 2, which is 2. Again, it will go inside this loop and 13 will be brought here. And I will be changed to I by 2, which is 1. So when I is changed to I by 2, which is 1, what is 1 by 2? 1 by 2 is 0. What does 0 have? 0 has the min value. So when you compare 5 with min value, 5 is not less than min value. So you come out of the loop and you put the 5 in location I, which is 1. So location I is 1. So element 1, 5 is put here. So I've tried to explain by writing small notes here, as well as I explain on the tree as well as with the array. So your insertion is done. It's not necessary the element will percolate up all the way to the root. It will percolate up till it finds its correct location, till the parent node is smaller than this element that you're trying to add. Now, deletion, it is the opposite of insertion, so we call it percolate down. So let me tell you why it's called percolate down. Let's come here. Okay, now I want to delete. In a heap, when you say deletion, it means that you can delete only the root node. Heap deletion means I can delete only the root node. And why is it so? Because the whole purpose of ordering the nodes in this way is to keep the minimum at top, or in a max heap we keep the maximum at top. So whenever I come, based on my requirement, if I'm making a mini heap, that means whenever I come to take an element, I always want the least element. Okay, so that is why this heap is also known as a priority queue. If you can store your elements in the form of a heap, they will be sorted in, they're not sorted when you look at it, but they are put in this tree structure in such a way that when you come to delete, you will come and you can straight away pick up the root element. And after that, the tree has to readjust so that the next minimum comes up. Okay, so when the next minimum comes up, next time you come, you get the next least element, which is you will get ascending order. Okay, so why heap is a priority queue? Because you can only delete the root element, and root element will always give you the minimum of all the elements, and as you keep on getting the minimum of all the elements, you can get the elements in ascending order. So that is why in priority queue, what do we have? We have elements, they can enter in any order, but when they leave, they have to leave based on their priority. So if these values represent the priority of your elements, when we come to delete, we will delete the element with the, let's say, the least priority or the highest priority. Depending on that, you will have a min heap or you'll have a max heap. So what do you do now? You have to come and delete 13. So I can delete 13 and move the least of the two upwards. Let's say I move 14 here. I've shown it with green arrows. Then I'll move 9 out of 19 and 21. I'll move 19 upwards. It's the least of the two. Then out of 65, 26, I move 19 here. But then I will create a hole here. And according to the structure property, you cannot have the last level not filled somewhere in between it. All the elements have to be on the left. So if you see here, I try and put the last element here if it is at the, if it does not violate the min order or heap order property. So I'll just explain in a while. Another thing is, when I delete 13, there's a hole here, and this 14 moves up, so the hole moves down. The 19 moves up, the hole moves down. 26 moves up, the hole moves down. Okay, then I copy 31 here. I'll tell you why and how in a while. Then this hole moves here, it kind of leaves the tree, so it's percolate down, the hole percolates down and the elements move up. Okay, so your delete is also known as percolate down. So what do we do in delete? In insertion, we went from the last level to the parent and to the parent till we found the correct location. In that was an insertion. In deletion, we'll move the other way around. So to delete something, if the heap is empty, you will not be able to delete. So you'll return the minimum element, which is at location 0. So deletion means I take out the element at location 1, put it in min element. Okay, this is what I'm going to return to the user because user performed a delete operation on the heap. Then I select the last element. Why do I select the last element? Because the basically the whole that is generated at the root should actually come down to the last element, because I cannot have any intermediate node in the last level empty. That goes against my structure property. So I start with 1, which is the root, and if you see, I changes in the previous case for insertion, I changed from I to I by 2. Here I changes from whatever value to its child value. The child value is either 2i or 2i plus 1. Will the child value be 2i or 2i plus 1? It depends on which of the children is least of the two. So first I allocate child variable with the value 2i. So if parent is I, child is 2. And then I compare the element, it's actually elements, the array that I've named, I've just written it in short. So child is the left child basically, and child plus 1 is the right child. So if your child is not equal to size, that means you are the child, when you say child is equal to the size, then you are talking about the last element. Okay, that should not be the case. If your right child is less than left child, that means the one that is going to replace your parent is going to be the right child, since it is a min heap. For max heap, this sign will change, it will be the other way around. So if right child is less, I do child plus plus. If it's not less, then child stays as 2i. This makes it here 2i plus 1. Now I don't straight away compare this and this. Okay, if you see, I am comparing the last element with the child. Why I am doing that? I'm comparing this last element with the child. Which child did I select? I selected the left child. In this case, left child is smaller. So I compare 14 with 31. Okay, I compare 14 with 31. If last element is greater than the child, then the child has the right to move up to the parent and not the last element. Okay, so I'll copy 14 to root location. Okay, that will be done. So when your child is copied to the root, that is 14 is copied in the root location, your hole moves down and we move down one level. Now we want to see who can fill this hole. Okay, so let me just erase this. Now your I, which was initially it was 1, but left child was less than right child, so it changed to, I've written some notes down here. Left child was 14, it was at location 2, and right child was 16, it was at location 3. 14 is less than 16, so we select the left child, which is 2i, which is 2. So after 14 is moved to the root location, I changes from I to the child value. So I is 2 now. So I is 2, it is still not equal to the size. Now what are the children of this location? The children of this location are 19 and 21. Again, the left child is smaller than the right child, so it will come out of the loop and it will compare this 19 with the last element. Last element is still greater than your 19, so 19 is moved up, the child is moved up to the parent here. Okay, then I changes back to, you see in the for loop, it changes to the child. So now the child was 2 and the parent now is 2 in second loop, and the child becomes 4 for the coming loop. So 4, if you see location 4, this becomes the parent now, 19, but 19 has moved up, so this is empty in a way. So the children of 19 are 65 and 26. In this loop, the right child is smaller. So when you enter this loop with this value for child, your right child is smaller than left child. Okay, so it enters the loop and child changes from the value of 26 here. It was 8. 2 into child was 4. 2 into 4 was 8. Now it is child changes to 9. And you come out and you check if 31 is greater than your 26. It is still greater, so 26 moves up. So 26 goes up. Now this space is empty and you cannot have the last level empty somewhere in the middle. So now after this, if your child was, what's the value? The value was 9. If you do 2 into 9, you go to 18. There is no 18 because the size of your heap is currently 10. So this condition becomes false and you come out of the loop. Once you come out of the loop, the last element is copied at the last I value. What is that I value? That is the last hole that was left out. And in our case, it was this location of 26, which is 9. And 31 is copied here. So this location here becomes empty. And 31 moves here. I've shown with arrows. This move of 31 to 26 is the last move. It is not the first move. Okay. So if I number this, first this, then 2, then this 3, and when you detect that there is a hole in the wrong location, you will move the last element there. Only if you go through all these conditions and check for every element that you move whether last element is greater than the child. Let me see if I can tell you an example where the last element is not greater than the child. I don't think I'll be able to find it in this tree, so we'll do that as an exercise later on. So I've written some notes here for you to understand what happens in each loop, what are the I values and what are the child values. So for heap, all you need to know is the two properties of heap order property and the structure property. Once you know that, you have to know how to implement, and in implementation the two important functions, insertion and deletion. We'll encounter heaps again later on when we do sorting. There is a sort mechanism which is known as heap sort. So like I said, heap is used as a priority queue because when you come to delete something in the heap, you always delete either the maximum element or the minimum element. So the application of heap is in priority queues. Also, you'll see later, because of the property of this tree, the number of steps required to do this or to alter the tree, it seems like it's a complicated job, but compared to the number of nodes in the tree and the number of steps you need to do insertions and deletions, the relationship between them is of the order of log n, which is log values are usually very small. So if your n is 10 to the power 8, log of n, which is log of 10 to the power 8, will be only 8. So for 10 to the power 8 nodes in the tree, you will be able to do insertion and deletion or this percolate up and down only in 8 steps. So the readjustment is very easy. Also, heap application is in priority queue. Another application of heap is that you use it for sorting. And how do you use it for sorting? I'll just give you a brief example of that with the last array figure that we have here. So what did we delete just now? We deleted 30. Okay, so we deleted 13 and we did the readjustments, and 14 moved here, then 19 moved here, 26 moved here, and 31 moved here. So our size, if you see, our size also decreases, and we do that here. We save the last element in this variable, and after saving the last element, which is at the last location, we decrement size by 1. So basically, when we are doing all of this work here, your heap is actually only this much. 31 is not counted. 31 we have saved in the last element. Now A simple way of sorting elements in a heap is to, let's say there are n elements in the heap. If you delete all the n elements one by one, you will get all the elements in ascending order. So when I delete first, 13 will get deleted, then 14 moves up to the root. Next time I come to delete, 14 gets deleted. If you see next time 16 will move up, then 16, so I'll get an ascending order. So heap sort is basically when you create a heap out of the elements, and then you delete all the elements one by one and you get a ascending order. So a simple way of doing that is, in this function that we just did a dry run for, 13 is deleted now. So when we reach the last step where we actually copy this 14 on the root value, before that we copy 13 here, or even in the beginning itself, what you can do is, when you are saving the last element 31 in the variable last ele, same time you can copy your root element here. So technically it is deleted from the heap because this is the size of your heap right now. Okay, so 13 is not in the heap, but you are reusing the same memory. You could save this 13 in another array, but this is a simpler way, or let's say a memory saving technique, where you put this 13 back here because the memory is still allocated equal to the capacity of the heap. So next time you delete 14, your heap size will reduce by 1, and then 14 will come here in this location, and so on. But if you notice, I said if you start deleting in the heap one by one, you will get ascending order. That is when you declare a separate array and then you store one by one. So I'll store 13 first, and then I'll store 14, okay, and so on. So I get ascending order. But if I'm trying to reuse the memory here, so I'll have 13 and 14. As the heap shrinks, the values come here. If you're reusing the same heap and you're using this logic, in the end you will have a descending order. If you're using a separate array to store the deleted values, you can store from 0 to n minus 1, and it will be in ascending order. So you have to just understand how it goes. So basically, if you do this, store it side by side in the last location which you have just kind of eliminated from the heap, you already have done your heap sort. Or if you declare another array and as you delete you copy it here, that is your heap sort basically. Okay, so that is all that we cover in heaps. There are other types of trees which we might do once we are done with the main basics of the course. What is left after heaps is a couple of storage management techniques, which is a bit of theoretical concepts which will be useful in your operating systems course later on. Then we have to cover hash tables, and then we have to do graphs. In graphs, what is important in data structure is the representation of graphs, but there are many algorithms that we can cover in this course itself, and if we are able to do that, it makes our next course, which is algorithm analysis, a little bit easier. And also, yes, I forgot, we have to do some sorting techniques. We just have to do the implementation of those, and in the next semester we'll be analyzing which sorting technique is good and which is more efficient. Okay, so that's the end of your heap lecture. I'll be mailing out an assignment on trees, and heaps would be part of the same assignment, hopefully. All right, thank you.